I'm Roger Frank from École des Ponts in France. It's really a great pleasure for me to chair this last session, well, the last session before the workshop of this afternoon. A real pleasure to introduce Dr. Suzanne Lacasse. Suzanne, first, I need to mention that she's an officer of the Order of Canada. So as there was a mistake in her gender, she's a knight and not, I forgot the word. Yes, but we can't change that. You're a knight now. Okay, an officer of the Order of Canada. Suzanne studied civil engineering at École Polytechnique de Montréal and MIT, Massachusetts Institute of Technology. After 12 years on MIT faculty, she worked for the Norwegian Geotechnical Institute, the well-known NGI, including 20 years as its managing director, 1991 to 2012. She gave the ranking lecture in the UK, the Terzaghi lecture in USA, the Coulomb Lecture in France, and the Carrillo lecture in Mexico. She's a member of the Académie des Technologies de France. In France, it's de France. In France, as you wish. As well as a member of the National Engineering Academies in Canada, USA, and Norway. Please, Suzanne, if you would like to come on stage. She's prepared for us a very, I think, presentation quite appropriate as a conclusion of this symposium devoted to Charles-Augustin COULOMB. Please, Suzanne.
As the shortest here. Thank you very much, Roger, for this introduction, and thank you, Alain, for inviting me to come and give this lecture. I'm very proud to have been asked. It's very nice to be in a French milieu, although I have to speak in English. The last paper in the Revue Française de Géotechnique, it attempts to put a perspective on the contribution of Coulomb work in today's research and consulting. And it's more a reflection. There's not going to be many equations. This is the type of equation that you will see most often in my presentation. But this is a clear proposition by Coulomb on the friction and cohesion on a sliding plane. And I say that this found application in design, and that's what I want to demonstrate to you. So the plan of presentation, I will have a few words on the applicability of the Coulomb material 250 years after the essay, and how Terzaghi verified this. It's an old document that I found at NGI. And then I was always been a bit disturbed by the fact that it has been published that there was a fundamental error in the Coulomb equation. So I will discuss this. And then finally, I call Coulomb the artisan of modern geotechnical engineering with some example or illustration where it's in our practice today. And so this is the basic Coulomb equation, and it's not an original figure, it's a fairly old figure, you can see from it. And it's quite simple. It has cohesion. It has the friction angle phi. And the definition of cohesion, as it's given in physics, because Coulomb was a physicist, is the act or process of sticking together tightly. Or it's the molecular attraction by which the particles of a body are united throughout the mass. So Coulomb was a physicist who discovered the laws that govern magnetic attraction and repulsion and invented the torsion balance. So can he also be still shaping the geotechnical engineering of today? He presented his essay in 1773 on some statical problems. It's a happy coincidence, in a way, that this 250th anniversary of the Coulomb essay is also the 100th anniversary of the principle of effective stress that was proposed by Carl Terzaghi in his 1923 German version of solid mechanics. In English, it came in 1925. And Coulomb noted that when friction and cohesion become zero, his equation gives the fluid pressure. He wrote about water pressure, although it's not in his equation, in section 10 of the essay. So he was aware that pore pressure played a role. But in those days, remember it's 1773, Coulomb did not have adequate apparatus for the measurement of the cohesion or the pore pressure, because Coulomb was the first to publish the measurements of under and shear strength in 1846, like 75 years later. So in an ideal Coulomb material, failure takes place along two sets of parallel planes, inclined at an angle, as shown here, alpha plus or minus 35 degrees plus phi. The planes form rhombic elements with two modes of failure in a test specimen. So a shear failure is likely to dominate in plastic ductile material, while strain-induced cracks may dominate in brittle materials. So in dilated materials, failure may take longer to develop. So this, I believe, the way Coulomb explained it, is the precursor to our stress path shown here for contracting. See, no, it doesn't. The pointer doesn't show on white. The contractive material is the one going down, the stress path going down, and the dilating material is the stress path going up. This is a modern test from 1980 or so. So a cut slope in a dilating material may start to crack at the crest, giving early warning. And the soil mass may gradually slump over a limited distance during reaching a new temporary equilibrium. Contracting material, on the other hand, can fail abruptly, without warning, and often at small strain, for example, sensitive clay. And already Coulomb hinted about that by talking about his materials. And this is a landslide that occurred in Norway in 2020, where 11 people died. Definitively contracting material. And, well, I don't have to show you, see the landslide which took so many houses. And already in the Coulomb theory, we could see the contours of modern geotechniques. And the simple model of Coulomb is very useful just to see how things behave. So the three states of design in practice that we have are easily represented. You have the at-risk condition, which is the lower line. Then you have the failure envelope, which is the upper line, and then the design condition. All of these represented with straight line. We know it's not exactly a straight line, but it's a very good tool to teach and to represent what is happening. Now, Terzaghi, who we all know, who was a determined person, he decided to verify the equation of Coulomb. And again, as I mentioned, this is data that we had at NGI of a course by Terzaghi in 1935, which you may know that Terzaghi legated all his material to NGI. So Bierum in 1959 found this and translated it from German to English, to Norwegian, and I translated it to English. And so this is data that has not been published before, which was very nice to find. That's the usefulness of libraries. Young people, libraries are great. So he tested the suitability of the Coulomb equation to represent the shear strength of cohesive soil. So these are the results that he obtained. This is part of the result. He had three sets of tests. One is completely undrained. One is quick. It's like what we call the Q test, old-fashioned test. And there was a very, very slow test to represent drain condition. And lo and behold, he obtained equations similar to Coulomb's. Now, by this time, the T had become a tau and the S had become a sigma, but it's the same equation with different friction angle measures. In those days, they measured friction angle very precisely. And Terzaghi noted, and this is a quotation from his German report to Norwegian to English, it's, if the shear strength T of a cohesive soil is determined for a given initial water content and under equal test condition, but for different values of the vertical stress per unit area of the horizontal shear plane, the results of the test in most cases can be expressed with sufficient accuracy by the Mohr-Coulomb equation. So this was the verification by Terzaghi of the Coulomb theory. But now intervenes stress strength anisotropy. Terzaghi observed that the most important difference in the test was the extent to which the void ratio was allowed to adapt itself to the change in stress on the sample. So if this adaptation was not fully completed, part of the force on the specimen was carried by the pore water pressure, or an increased pressure in the pore water. Terzaghi therefore emphasized that Coulomb's equation gives the relationship between tau and sigma, or T or S, for soil specimen, but that one needs to consider initial void ratio, testing apparatus, drainage condition, test procedures, etc., what else may come. Thereby, using Coulomb's law, Terzaghi introduced the concept of stress-induced and inherent anisotropy for clays already in the 1930s. Coulomb provided the general relationship for shear resistance. The practitioner, you and me, the theoretical modeler, the researcher, they still have to determine which test conditions are the relevant ones. This is still true today, and this is probably one of the major mistakes we do in design. So how many times I'm older, so when I offer mentor young people, and how many times I tell them, well, how did you obtain the shear strength? Oh, I just, somebody answered me from Wikipedia. So that didn't pass. But choosing the Coulomb value C and phi have to be related to what you're trying to model. So it's important with the relevant test, the relevant procedure, and the stress history or stress path. And here's an example of a classical stress path for drum and clay in triaxial compression, not a stress path, stress strain curve in compression and in extension. And as you see, they're very different, but they follow the C and phi law of Coulomb. And this very classical way of analyzing an embankment, where we model the circular slope failure in this case with the triaxial extension test, triaxial compression test, and simple shear test, they also follow Coulomb law, but the numbers or the parameters are not the same because of different stress paths. Terzaghi in 1935 even suggesting adding an index to make it very clear that the validity of the Coulomb's equation depends on the conditions analyzed. Terzaghi suggested the Coulomb equation with a D would indicate drain or slow test, and with an S, it would indicate that the shear force is increased so rapidly that the void ratio of the soil remains unchanged. And he even suggests an index DS for the condition in between. Now, maybe the profession should have followed this, because today this is one of the things, again, that we often mix in practice. From then on, Terzaghi's and researchers at MIT, now this is not complete, but I use my background where I was educated and the people I talked to. So there was Lamb, and there was Taylor, and Whitman, and Ladd, and Einstein, and at Harvard, Casagrande, and then Imperial College, Kempton. They followed these tracks and did a lot of experimental work and check or confirm the validity of Coulomb's equation under different stress and strain conditions. Each of them stressed the necessity of replicating the in-situ condition in the laboratory. Even in the UK, where Coulomb's work has been critically discussed, which we will see afterwards, critical state soil mechanics agrees with this Coulomb law. So I will look into it, but is there a fundamental error in the Moore-Coulomb equilibrium? So I will present the hypothesis of an error, and which was based on the Taylor text, and what Taylor said, and then my own conclusion on the error. So Schofield in 1998 and 2005, and other publication, suggested that the error rests on the observation that Coulomb's equation omits a component of strength called interlocking. The interlocking refers to the term mentioned first by Taylor in his book 1948 and in some lectures before that. Schofield wrote that the Coulomb theory with a straight envelope takes no account of strain boundary conditions, and that Coulomb wrongly interpreted strength data to get the straight line, and that Coulomb, when considering failure on an inclined plane, assumed that the slip direction was the same as the direction of the plane. Schofield used as argumentation that Taylor's test showed that the peak strength of the sand was equal to a combination of an angle of friction plus a term of interlocking. And Schofield added mistaken interlocking for cohesion. Terzaghi later, and Vorslev even later, attributed peak strength of their reconstituted stiff clay to surface chemistry among salt grains rather than real friction. But that last statement is certainly not a Coulomb error. It would be an error of Terzaghi or Vorslev's. But what did Taylor say in 1948? And this is a poor drawing, but that is taken from the original Taylor book, the very, very first, which was handwritten and such, where he illustrates his check of Moore-Coulomb line. And then you have the figure there, and below the figures, it's his original figure. He said, plot illustrating the rational interpretation of Coulomb's empirical law. And the data, the law by Coulomb is the, let's see if I can, no, the point doesn't work. It's the dash line, the straight line, whereas his test on the sand is a curved line and then goes a bit up, a bit bizarre at the top. And I find the two lines are really quite close. So, and in his text, Taylor agrees with Coulomb. Taylor did not describe Coulomb's theory as an error. On the contrary, Taylor called the Coulomb parameters as empirical coefficient and mentioned that different conditions should be accounted for by the engineers using the Coulomb equation. He added, curves of the Coulomb type are representative of the strength of a given soil when it has been subjected to a given magnitude of precompression. At different depths in a deposit, there usually are different amounts of precompression, thus a different envelope may hold for different depths. So he was already talking of using Coulomb, but in a normalized manner in terms of effective stresses. Okay, try this. Okay? Okay? Yeah. So my interpretation is that Taylor's paragraph validates Coulomb's strength theory. And there are two recent papers, one in 2015 by Christian Becker and one by Berlin in 2008, and they reiterate the same. And I've put their pictures here. You might not know them. Well, everybody knows John Berlin. And they reiterate that Taylor's concept of interlocking is not inconsistent with Coulomb's theory, but complementary. It's a sign of progress. It brings new results from Taylor's research. For Coulomb, shear strength was the sum of friction and cohesion. For Taylor, after reflection and new testing of sand, shear strength was the sum of friction and interlocking, and not necessarily perfectly linear. So, one conclusion, my conclusion, the so-called Coulomb error, is that the vocabulary has changed or expanded over 250 years is expected and normal. That one refines the components and physical understanding of soil and rock strength and resistance is also expected and normal. It's 250 years. We have to do some progress. And then that one finds through testing, observation, or reasoning additional factors and subclasses of condition that affect soil and rock resistance is also expected and normal. So to suggest that the Moore-Coulomb equation wrongly interpreted strength data and developed a faulty relationship is, in my mind, questionable. To declare a 250-year-old theory to be in error because part of a component of the resistance is not fully explained with today's terms, and the understanding has changed, and given the experimental facilities available in the 18th century, I think is not a fair assessment of what Coulomb said in 1773. So another conclusion I have is I find that Coulomb's principle was the precursor for developing the tools to meet the engineering profession's responsibility of ensuring the safety of people and preserving material property and the environment. Through Coulomb's theory, the engineer can become intimate with the foundation soil and continue to rely on experience, peer review, and simple hand calculation. I'm all for finite limit, etc. But with this, you can do some simple calculation and check that you're in the right order. So in my mind, Coulomb, without doubt, laid the groundwork for the understanding of soil and rock resistance. Now, just a few examples of how Coulomb is influencing today's practice. Well, the profession has greatly evolved. 100 years after the statement effective stress, and the principle of effective stress really changed soil mechanics. With the computer and artificial intelligence revolution, the profession is today endeavoring to develop machine learning application and messaging multi-data sets and everything. I myself am involved in that. But that does not, and there's an example of a training of a machine learning model. That's all right, but still, it's not the whole story. The data will still have to observe Coulomb's law. The profession is a paradigm shift from dedicated verifiable data towards vast numbers of measurements in anonymous distributed system, like, for example, digital twins in the laboratory. These new developments will be helpful, but the fundamentals must not be forgotten. So observing the Coulomb's principle remains an absolute requirement for the teaching and practice of engineering. Fundamental understanding should not take a back seat to numerical development and AI interpretation. I'm not against it. I just say you have to also keep the principles. So the Coulomb's equation has found applications with everything we do. I just have taken 4 examples, and the one is in praise of testing, or laboratory and in-situ testing. Coulomb was an experimental scientist. He wrote about friction and cohesion. And he also wrote, only experiment can help us to decide the reality of the different causes of shear resistance. And following Coulomb's philosophy, Carl Terzaghi set up a laboratory to measure soil and interface properties everywhere where he worked. He set one up in Istanbul, then at MIT when he went first, and then at Harvard. And I think I have it. Yeah, that's the laboratory at MIT in the old days. It had been clean. It was not that clean when I went there. Many of the remarkable advancements in geotechnical engineering are due to Terzaghi, Kazagran, and Vorslev's experimental work in the MIT and Harvard years, and also in Pearls and Cambridge. But again, I limited it to what I knew. But then I can show you the picture what today laboratory looks like. Now, there are not too many as big as this in the world, but look at the type of equipment we have and the organization and how things just roll in and get tested, and our constant temperature and freezing room and hot room if you need them. We can't compare we can't with justice say Coulomb was wrong when we can use such facilities. So, but if only clay deposits could talk, like the Chaffalai clay, that's a very soft clay in the United States, and the New Orleans flood protection levee foundation, or the sensitive clays in Norway, in which you saw a landslide, they would tell us how important it is to thoroughly understand the geology and the stress history of a deposit, and then apply Coulomb's equation. Geotechnical engineers, they need to have a sense of how soil behaves by touching and feeling a sample. Honestly, I've done that all my life, and it helped me a lot. And understanding why the in-situ and laboratory tests are needed to determine quantitative soil properties, the stress history, and decide at the end of the soil profile and the strength. And these in-situ conditions are then used to apply Coulomb's equation. So I took an illustration from Chuck Ladd, who was my advisor, and from his Charles-Augustin lecture, where he very carefully plotted all the data by hand, and then look at the stress history, the effective stress, and what was the pre-consolidation stress, and then interpreted the shear strength profile. And that, I think, is good practice, even with all the good things we do with the computer. The second aspect, design of offshore installation. You may not know, but I've worked many, many years with offshore structures, the gravity base and the pile foundation, and now with windmills. And the yield stress design of Coulomb is also part of the solution for newer foundations like these, although many new factors come in, but that's all right. That's the advancement of our science. So the behavior of sand, silt, and clays under cyclic loading, it was not a topic in 1773, is still represented today with stress paths, with C and phi, and we use Coulomb's law. The behavior of the working stress range, what we call serviceability limit state, is key to the solution for offshore design. And the soil resistance depends on the mean shear stress level and the degree of shear mobilization using Coulomb's principle. And it's probably difficult to read, but there's a part in the essay that I believe is the precursor for reliability-based design and the effect of uncertainties on the computed safety. So this is an excerpt of a translation by Hyman in 1972, and I have taken some parts of it. In his essay, one sense that Coulomb is aware that many factors are important and may affect the soil resistance, and that they should be considered to ensure that the design is safe enough, or today we would say reliable enough. Coulomb refers to the effect of pore water pressure, moisture content, potential blocking of drains, that's very important for landslides, presence of ice and fissures, it was for a retaining wall. And then he also lists the aspects that are not accounted for, like the quality of the material that's recovered and the freeze-thaw effect, and even on the model that's used to calculate it. And that's in 1773. So if you read the text, he's already talking about reliability and how good is your calculation. So and in his method, Coulomb makes a value judgment of what should be an acceptable design. So his acceptable design, given the aspects that one cannot account for, ignorance of, or uncertainties, that would lead to an overestimate or an underestimate of the underlying shear strength, and then leading to the reduction of the uncertainty for the safety factor. The observation by Coulomb can be interpreted as an indication of the uncertainties involved in the calculation and their effect on the calculated safety margin of a retaining wall. So, at least as I read the document, I find it a confirmation that they knew that there were many other things that one should account for. And I am very impressed because that's what we're trying to convince clients about when we do reliability design today. So this figure, which is very well known, which shows a portion of what is a failure probability, you have the distribution of the load on the left and the distribution of the resistance on the right, and where the two uncertain distribution overlap. That is how wide the failure probability can be. So Coulomb, without thinking about it, but I'm sure he knew about statistics, he already hinted, be careful, there are other things that come in addition to my equation. And then in standards and guidelines, they also use many of the concepts of Coulomb, and many of the requirements are expressed in terms of friction and cohesion. And naturally, they say you have to look at the stress system. You have to look at whether it's a horizontal failure or a 45-degree failure. But that's all right. Coulomb gave us the first idea, and then we completed with new knowledge. So I come to my summary, and this is a repeat of the lecture by Professor Salençon. I'm going to read it in French, rather you have it in English. The English is on the right. Right. But he said, de rendre les principes dont je me suis servi assez clairs pour qu'un artiste un peu instruit, this is us, an artist, and put les entendre et s'en servir. Ce mémoire n'était d'abord destiné qu'à mon usage particulier, only for me, says Coulomb, dans les différents travaux dont je suis chargé par mon état. Si j'ose le présenter à cette académie, he wanted to give his knowledge to other people to move forward with it. So I think that was very noble. So the value of Coulomb's work lies not only in the groundbreaking discovery he did in the 18th century, but mainly in the development to which this discovery led us over the next 250 years. So all the work that we've done are a consequence that he stated the equation first. He probably did not foresee the significance of his work for an entire branch of civil engineering and for resource and infrastructure development in a worldwide scale. So his objective was to share the knowledge and hope that it would come to use to someone who in the future would be likewise interested like him. And that's again us. So he was talking to us. So I find that Charles-Augustin COULOMB in his essay reached his objective. Naturally, he could not imagine that we would be installing 400-meter high offshore structures, or that we would be having suction anchor moving 40 meters in the ground, or that we would have very elegant bridges and long underwater tunnel. Maybe he would have been scared by these developments. But at least he provided us the tools so that we could work with to do these developments today. So Coulomb's equation, together with the effective stress principle inspired by to Carl Terzaghi by Coulomb's work, are the mainstay of geotechnical practice. Coulomb's work continues to inspire new generation of researchers to look into improved and novel interpretation of the shear strength of soil and rock. And we will find more things in the future, and that's fine, but we will still rely on Coulomb. Coulomb's contribution to the design of structure deserves the attention and recognition it has received. There have been new developments since, but the origin of the understanding was with Coulomb's equation. That the profession discovers limitations, additional influential factors, extensions, does not invalidate the theory, rather it validates it and accentuates the outreach of the yield design approach in his 1773 essay. So in closing, Gustave Eiffel named 72 engineers and scientists in the Brotherhood of the Eiffel Tower. We were just beside it yesterday. It's on the first floor, first level. And Eiffel wanted to outline the importance of teamwork and cooperation in engineering. That's what he wrote. The 300-meter high Eiffel, built in 1889, is a triumph of human ingenuity and engineering collaboration. Eiffel did not think of the tower as his own. When Eiffel dedicated the tower, he recognized the many contributors to French science and technology during the past 100 years. He put 72 names on the side of the tower on the first level. Unfortunately, I don't have a picture of that, but the first time I go to the Eiffel Tower, I'm going to take a picture. But who were those scientists chosen by Eiffel to be members of the Brotherhood of the Eiffel Tower? 2 were agronomists, 6 astronomers, 9 chemists, 4 industrialists, 1 geographer, 15 civil engineers, hooray, and 17 mathematicians, oh, that's good too, 2 physicians, that's just the medical doctors, 2 mechanical engineers, 2 mineralogists, 1 biologist, and 11 physicists. And Coulomb's name is there, together, I just chose a few, the best known, together with Ampère, Becquerel, Breguet, Carnot, Cauchy, Coriolis, Foucault, Fourier, Lamé, Laplace, Lavoisier, Navier, Poisson, and Tresca, just to name a few of them. And there are about 60 more of these names. So Coulomb, he was a physicist by training, but he was also an engineer. Being an engineer requires specialized knowledge, an insatiable interest in how things work, and a knack for solving problems. Charles-Augustin COULOMB mastered all aspects, and this gave birth to the basic for the science of today's soil mechanics and geotechnical engineering. So we should be thankful that he showed us the way. Thank you very much.
Does it work? Thank you, Suzanne. Thank you for showing to us the richness of Coulomb's equation and also all the consequences on the modern geotechnical engineering and soil mechanics, and also helping us discover a little bit more the Eiffel Tower, by the way. Questions?
Thank you very much, Suzanne. What a splendid, wonderful lecture, which I'm sure we've all learned a great deal from, and I think most of us can only support what you've said in your last few slides, in fact, all the way through. I just wanted to dwell a little bit on the understanding of soils, in the sense that I think Schofield was talking a lot about, in his mind, about remolded soils, which are not very aged. And I'd like to just draw a link between what Peter Robertson said yesterday, looking at his QTN and his IG plots, where he displaced a line across to account for microstructure, which, when we then go back to what Coulomb said was cohesion is about sticking together tightly or molecular attraction. So I think there's a difference between those two things, where with a remolded soil, you don't expect to have any cohesion at all, and with an aged soil, you do. And I think there's lots of other misunderstandings about how you use Coulomb's law, or there's lots of flexibility, shall we say, how you use Coulomb's law to attribute interlocking or suctions or root reinforcement to whether you add more on the cohesion or whether you add more on an increased friction angle. And I think that's something that we can look at and talk a little bit about in the future. But I very much like the way you had attacked the problem that you took on, and thank you very much for that.
Yeah, but it's, you know, Coulomb is a model, and so in the model C can be 0. So, and then we all know that a very low stress maybe the envelope is curved. But I find that that's a derivative of the theory. It's a case of the theory. So I don't disagree with what you say, well, it's rare that we see a perfectly normally consolidated soil in terms of clay, except if you reconstitute it yourself. We often see cohesion, or we measure suction in an over-consolidated soil. So there is something there. So.
Sorry, can I add that C can be 0 and phi can be made of several levels. Yeah. When Taylor is speaking of interlocking, as years ago I was reading what he was writing, working on dilatancy, isn't the interlocking the dilatant part of the phi of Coulomb? So it's made of this sort of interlocking, I would say, aspect. The grain to grain, of course, the basic one is grain to grain friction, and then adding this different effect. So perhaps this was...
You're right. In Taylor's book, he has like 7 or 8 pages of explanation following the old figure I showed you, and the degree of interlocking, and then the curvature is changing phi. from different tests. So there is something there, but my point was just that Coulomb was a very good starting point to develop further.
And what we're doing now to tailor, and then also the work of dilatancy by row, by the way, etc., is to in fact, or still going on, I don't know, is to sort of splitting the phi angle of Coulomb in the different aspects or something like that. Well, it's my understanding. Sorry, my question was, is it a good understanding? So I need a question.
Yes, I think it's a good understanding. But I think that's the richness of the model that he provides to us. We can discuss it, and while still believing in the basic principle, we can change it. Isn't that how the models in finite elements evolved too? I mean, when I was a student, it was elastoplastic.
Yes, thank you very much, Suzanne. Listening to you, I feel that it's just as if in geotechnics, older theories include new ones, whereas in physics, for example, newer theories include the old ones. Don't you think so?
No. I don't know if I agree completely with that. I value the new theories and all the new models, but as long as they don't contradict, where they expand on Coulomb's theory, then I would say it's a new theory, and it includes Coulomb's hypothesis, let's call it that way.
Other questions or philosophical remarks? Okay. Thank you very much, Suzanne. This was outstanding.
Thank you for having me.